So very few, right? Okay. So Markov modeling is a very, very strong technique that I think you need to be familiar with. I didn't put a chapter in this course for Markov modeling because it's very mathematical. Yeah, it can be abstract at times. That's why I didn't want to. So I'll just mention it that we will be using Markov models. And if you're not familiar with it, you need me to provide you more context, then I can dig out some materials and I can provide to Professor Nangia, who can distribute to you. Yeah, just let me know. So first of all, we are going to start with the frequency and duration technique. Remember yesterday we said, or I asked you the question, from your perspective and my perspective, what is more important? Yeah, somebody said revenue, but what we eventually said was, from our perspective, we want to know how many failures will take place in a given time period, and whenever there is a failure, how long will it last? So number of failures is the frequency, how long it will last is the duration. So from our perspective, frequency and duration are more important than anything else, like LOLE, the loss of load expectation, which we shall study tomorrow. Yeah, so that's why I want us to learn a little bit about the frequency and duration parameters, because it helps us to understand the systems a little bit more, particularly the repairable systems or maintained systems. So we want to find the time-dependent reliabilities and steady-state reliabilities of the various systems, and the frequency and duration, we are going to call it F and D. Yeah, everybody knows F and B. Yeah, so now I'm introducing F and D method, which will allow us to calculate the frequency and duration parameters using Markov models. Okay, so let's look at this Markov model of a single state component. Sir, it's not working again. Even this guy is hungry, I guess. Can somebody make it work? Markov model. Consider the case of a single repairable component. One component which can be repaired. Okay, we are looking at repairable systems now, not mission-oriented systems. So this is the component. The component is operating. We call this state 0, or the component has failed. We call this state 1. Okay. So how does it go from state 0 to state 1? It goes through this failure rate called lambda. And once it is in this state, how do you bring it back to the operating state? Through repair, right? So this is the repair rate. Mu is the repair rate. Lambda is the failure rate. Okay. So the probability of being in this state, P0, probability of being in state 0 is given as mu over lambda plus mu, which is equal to m over m plus r. So m and r are operating times and repair times respectively, and lambda and mu are failure rates and repair rates respectively. Now you may remember that m is the mean time to failure. Yeah, I mentioned earlier, small m is used to denote the mean time to failure, MTTF, and this r, small r, is called mean time to repair, MTTR. And of course the total of m plus r is MTBF, mean time between failures. It's also the cycle time, meaning one cycle is operating plus failed, next cycle operating plus failed, right? So the mean time between failures is m plus r, which is equal to 1 over f, where f is the cycle frequency. Now the mean time between failures we do not use very much in power engineering, in power systems. Why? Because the lambda, as I mentioned earlier, or the mean time to failure is very large compared to the mean time to repair. Yeah. Remember I mentioned that lambda is a very small number, one failure per year typically, and mu is a very large number, 500 repairs per year, right? So if you take the reciprocal of that, then the mean time to failure m is 1 over lambda, remember? The mean time to failure is 1 over lambda. Similarly, the mean time to repair is 1 over mu. Yeah, so you will find that lambda is small, mean time to failure is large. Mu is large, but the repair time is small. So they are each other's reciprocal, so to speak. Okay? And the mean time between failures in power engineering, we don't use that, but for electronic components, this is used, because when the system fails, you don't normally repair, you will replace, you will put in a new component for electronics. But for power systems, we can't afford that. If our transformer fails, our friend was just mentioning, after 15 years, at least they try to repair it, right? So this is the cycle. The component is up and then it goes down, and then it is up and then it goes down, right? So one cycle is operating and failed, right? This is one cycle. Cycle time is T, which is 1 over F, right? The time and frequency are each other's reciprocal, as you know. So mean time to failure, 1 over lambda. Mean time to repair, 1 over mu. And the total frequency is the reciprocal of the time, which is 1 over m plus r. So we can make some substitutions, and we find that lambda times P0 is equal to mu times P1. Now what does that mean? Lambda times P0, that is the probability of being in this state multiplied by the rate at which the component leaves this state, correct? That is what it is, P0 times lambda is equal to P1 times mu, the probability of being in the failed state multiplied by the rate at which it goes away from that state. So we find that the frequency, probability times the failure rate or repair rate, is nothing but the frequency. So we find that the frequency of being in this state is the same as the frequency of being in this state. Frequency is the same, probabilities are different, the rates are different, but the frequencies are the same. That's the conclusion we arrive here. Frequency, probability of residing times rate of departure is the same as frequency, probability of not residing times the rate of entry. Yeah? So the two are one and the same. So the frequency of encountering an operating state is the same as frequency of encountering the failed state. The two frequencies are the same, I repeat, not the probabilities of the two states, correct? So why do we need the frequency and duration technique? You look at these two systems, a comparison will tell you that there is this system where the failure rate is lambda and the repair rate is mu. And there is another system too, where it fails 3 times more, but it is repaired 3 times faster, correct? So if you find the probability of being in this state, probability of being in this, the probability is mu over lambda plus mu, first system, and probability of being in this state, same as probability of being in this. So sometimes the probability itself is not enough to describe the system. That's why we need more parameters, such as the frequency and duration. So that's the reason why we also want to learn about frequency and duration. As luck would have it, or at least from a student perspective, we should always say luck, because the frequency and duration is not very popular, because it involves more data. We need data on lambda, we need data on mu. And if it is just one component, it's easy. But if it is 2 components, 5 components, 10 components, in the case of a power system, we have hundreds of generators. And therefore, the Markov model is huge, and you need a huge amount of data. Say that number?
Minimum set of parameter, set of the data is required to drive this.
I mean, I have said this a few times, that when we have large number of components, then each component you want to model as minimum 2 state and maximum 3 state. One of the states can be derated state. And then if you do the Markov modeling technique, then you can expand all this and you can write a software program very easily. The number of states will be very, very large for a 100 generator system. So we use some approximations, as I will show you either tomorrow or the day after, how we reduce the number of states and do the calculations with some approximations, but not losing the accuracy by too much. Okay? So that's why the frequency and duration is good, but because it also entails complex data, therefore we are not going to learn at this stage. So this is just a small example to show you that the system was operating for M1, then it was down for R1. then it was operating for M2, down for R2. That's why I remember mean time to failure is suppose 1000 hours. Doesn't mean that the component will fail every time after working for 1000 hours. That's the same question you were asking me. The lifetime is 25 years for the transformer. It failed after 15 years. It could have failed after 1 year. because this is all stochastic. Yeah? Nobody can tell you when it's going to fail. But we can predict based on the data that the manufacturer has provided as to, what is the anticipated failure rate. And then we know roughly that it might fail, but it could still oppose that. Yeah. On an average, if you allow it to fail over a long period, then that average will be correct. That is all that means. That's why we talk about mean time to failure and lambda, the failure rate. Yeah, these are all mean values and they have a distribution. It's not that they don't have a probability distribution, but at the end of it all, we have to use a number which you generate based on statistical data or your predicted forecast, right? So this is just a simple example showing you, operating failed, operating failed, operating failed, and the timings are given, and then we found what is the mean time to failure, M1 plus M2 plus M3, and the mean time to repair R1 plus R2 plus R3. So we found that the lambda is 3.02 failures per year. You would have expected lambda to be 3, isn't it? You would have expected lambda to be 3. Why? Because it failed here, it failed here, it failed here. You say, oh, 3 failures? But the failure rate is not 3. The failure rate is 3.02 failures per year, right? So it'll be very close to that, but not necessarily that. This is how we can actually estimate the failure rate and the repair rate. Mu is the repair rate, number of repairs per repair. Number of repairs per repair, right? Usually must be a large number for your system to be quite reliable. Okay, and then the cycle frequency will tell you that, the frequency is 3 per year. That's correct. The frequency is 3, but the failure rate is 3.02. So the frequency and failure rate can be slightly different. Yeah, that's why the frequency and duration technique sometimes is a little bit more data driven. Okay.
Is there any benchmark like median time to failure?
You are a benchmark guy.
So that is the standard we can use to make other people on the higher level understand the thing properly. So is there any benchmark like median time to failure?
For mean time to failure?
One is mean time to failure, which you are referencing. Is there any benchmark like median time to failure?
Median?
Median.
Not that I am aware of. I know of median salaries and mean salaries.
Sir, exactly. I mean, averages and means are very, they skew the data very well. Sometimes the median gives a better picture of what the present situation is.
Not for continuous distributions. I think the mean time and the standard deviation are the ones that are used, not the median. Yeah. Okay, so we will just study one more technique if you allow me 10 more minutes and then we'll stop, or you want me to stop now?
No.
Yeah, okay. I think all of them here are very excited, or so I believe. Okay. So just the frequency balance approach, which is one of the techniques which shows you how to calculate the frequency, the probability, and the duration as well. So we just learned that the frequency of leaving a state is the same as the frequency of entering a state, right? I showed you using a one component system. Yeah, we have already learned that. So let's go to a two component system. And this is the Markov model of the two component system, where component 1 is up, component 2 is up. This is called state 1. Then component 2 can fail by its failure rate lambda 2. So component 2 is down, but component 1 is up. So when you enter this state number 3, what are you doing? Are you sitting on your laurels? No, you are trying to repair component 2 and bring it back up, correct? So that is where the repair rate of component 2 comes in. Now, this is one way that the system will have one component down. There is another way. Component 1 may fail and component 2 may still be operating. So this will fail by its failure rate lambda 1, and then while this happens, you are going to try and repair component 1 and bring it back to state number 1. Yeah. Now, From here, while you are trying to repair component 2, component 1 can fail. This is what we call overlapping failure. Yeah. So you are trying to repair component 2 and go this way. But while you are doing that, component 1 also fails. Now both of them are down. Yeah. Similarly, when you are in this state, you are trying to repair component 1. Meanwhile, component 2 also fails. So you can be in this state. So this is the 4-state model of a 2-component system. Now, in case you are wondering, and I'm not sure if you are, because you may be thinking of lunch, but there is another transition that can take place from here to here, right? There can be a common cause failure, meaning both the components can go directly down. That's what we call a common mode failure or common cause failure. So the deeper we go into reliability evaluation techniques, you will find that we'll need more and more and more sort of information. So for now, we are just trying to avoid it, but just to let you know that that transition is possible. As long as you have the data to model that transition, it should be included in the model. Otherwise, this is the general model, okay? So I'm going to write some frequency balance equations. Remember, the frequency of being in state 1, yeah, being in state 1, departing, and frequency of entering is the same, right? So let's go back to this. State 1. What's the frequency of leaving state 1? It's the probability of being in state 1 multiplied by lambda 1 plus lambda 2, correct? The total failure rate outside state 1 is lambda 1 plus lambda 2. And the probability of being in state 1 is P1. So P1 times lambda 1 plus lambda 2. So that's the frequency of leaving the state. What about the frequency of entering state 1? So it can enter this way or it can enter that way. So how does it enter this way? P2 times mu 1. And how does it enter this way? P3 times mu 2. Yeah, so you add the two numbers and that's what you get. P2 times mu 1 plus P3 times mu 2. So similarly, you can write the other equations for state 2, state 3 and state 4. But these are only 3 independent equations. When you write these 4 equations, only 3 of them are independent. In other words, you can't find P1, P2, P3, P4 by using these 4 equations. You have to use another one. Yeah, and that is P1 plus P2 plus P3 plus P4 must be 1. There's only 4 states in the system and therefore the total probability can never be more than 1, can never be less than 1. Okay, so that equation plus 3 of them you use to calculate P1, P2, P3, P4. That's how we calculate the frequencies, the probabilities using the frequency balance approach. And of course, once you know the probabilities, then the frequencies are obviously known. You can calculate the frequency either using this or this. Yeah, and once you know frequency, you know the probability, you can find the duration. So that's how we go from probabilities to frequency and duration, or from frequency to probability and then find the duration. Okay. So just one example and then we'll probably call it off. Consider this system where there are 4 states. This is described as a up state. This is also an up state. This is described as a down state. This also a down state. Now, why do we just use down, down, up, up? Because this is the way that system is meant to be operating. So I'm not giving you the details of the system, but the Markov model is telling us that these 2 are considered success states. These 2 are considered failure states. Okay? And the transitions are known, given to us. Transition from state 1 to 2, transition from state 2 to 3. And it's only one way. It doesn't have to be 2-way, meaning that we are not repairing at all. It's possible. Right? Similarly, the transition from this state, it can go up through these 2 ways, and when it is down, it can still go to this state, which is also a down state. Yeah. So that's the process, that's the way that this particular system operates on. And you are given the transition rates A, B, C, and D, and E. What is the probability and frequency of encountering the failed state? Probability and frequency of encountering the failed state. So draw a boundary around this. Draw a boundary around this, right? That's what you want, isn't it? Because these 2 are down states. So let's look at this boundary. What will be the frequency? Let me ask you this question. What is the frequency of being in the down state? Remember just now we talked about the frequency balance approach. Frequency of entering is equal to the frequency of leaving. So suppose you take the frequency of leaving around this boundary. How is it leaving around this boundary? It is leaving this way and this way, correct? So therefore, that will be P4 times D plus E, correct? We know D plus E, we know the D's and the E's, but we don't know P1, P2, P3, P4. So the essential problem is to find P1, P2, P3, P4 by using the frequency balance approach. So what's the frequency balance approach for example, for this state? It is P1 times the departure, P1 times A is equal to P4 times E, right? Similarly, you can write for this state, this state. So the equations I have written for you here, yeah, the equations are, and of course you have to use another equation because these 4 equations are not independent equations, only 3 of them can be used. So from these equations you can find P1, P2, P3, P4, yeah, I have done all the calculations for you, and these are the numbers that we come up with. So we can find all the probabilities and then we can find the frequency, yeah. So the frequency of being in the down state is P4 times D plus E, yeah. So that's how we can find all the probabilities and the frequency of being in the down state or the frequency of being in the up state. I didn't ask you that question, but what's the frequency of being in the up state? You can draw a boundary around here, right? You can draw a boundary around here. How is this boundary being entered? How is this boundary being entered, right? So it's entered from here only, right? It's entered from here, these 2 ways, correct? So it will be P4 times D plus E, it's the same. Okay, so I think we can stop here. Let's see what I have next. Yeah, approximate system reliability evaluation. So we are going to go back to some more techniques to calculate the series, parallel and non-series parallel, and we are going to revisit the minimal cut set method again. So we were talking about the frequency balance approach when we finished yesterday. Prior to that, we also learned the frequency and duration method. And what we found through the frequency balance approach was that the frequency of leaving a state is the same as frequency of entering a state. And using this approach, we found the probabilities of being in each of the states. So for example, we can find the probability of being in state 1, 2, 3, and 4. And we also did another example, if I recall correctly. Yeah, this particular example where we found the probabilities of being in states 1, 2, 3, and 4. And you were asked to find the frequency of encountering the failed state as well. So we said that this is the failed state, the down, this boundary. If you draw a boundary around this, then that's the failed state, right? The down state. And the frequency of entering that state is the same as frequency of departing from that state. So if you take that boundary, then you can see what are the transitions into that boundary. And the transitions into that boundary are only here, right? The transitions into this boundary is only here. So it is P2 times B, yeah? It's P2 times B. So that will give you, good morning ma'am, that will give you the frequency of being in the down state, frequency of being in the failed state, correct? Okay, everybody with me? Okay, good. So that's where we stopped, yeah? The frequency of being in the down state is P2 times B, as I was just explaining just now. Alternatively, of course, you could look at the frequency of leaving the down state. The frequency of leaving the down state is through E and through D, yeah? So P4 times E plus P4 times D, it's the same as P2 times B. Frequency of leaving is the same as frequency of entering. So we finished this, and now we are in a position to look at what we call as approximate system reliability evaluation. I mentioned a few times already over the past couple days that engineers, they don't like to do things in a very detailed manner, because sometimes things are so complex that you are so mired in the complexity that you can't get any feasible results. So it is always better to make some approximations which are reasonable. You don't want to lose the accuracy, yeah? And yet you don't want the analysis to be so complex that in the end you don't get any meaningful results. So that's the purpose of using approximations. So we have two components here in series. The first component has failure rate lambda 1 and repair rate mu 1. And the second component has failure rate lambda 2 and repair rate mu 2. Remember, we are dealing with repairable systems. We are dealing with continuously operated systems. We are no longer dealing with mission-oriented systems. And then we want to combine these two in series. I mean, the system requirement is that these two components operate in series. So we determine an equivalent component, and the failure rate of that component is, it should be lambda s series and mu s. Yeah, so somehow, I don't know, comes up as 3 there. So how do we calculate the equivalent failure rate of this component and the equivalent repair rate of this component? That's what we are trying to do now. So let's just look at some of the basic equations. The probability of being in the up state, that means the system is operating. So if we go back to this diagram here, both of them are in series. You remember the 4-state model, component 1, well, let's go back there, I think, maybe easier. Yeah, this model, we have two components. Both the components are up, or one is down, or two is down, or both are down, right? So if we want to have series operation of these two components, then this is the only up state. Am I right? This is a down state, correct? One component down means it's failed. Series components, remember? So this is failed, this is failed, this is failed. Yeah? So these three states are down states, and this is the only up state. So what is the probability of the system being in the up state, in the operating state? Is the probability of component 1 up multiplied by probability of component 2 up, isn't it? Because both the components operate independently. The failures are independent, remember? They're not dependent on each other.
Just what's the meaning of component?
Component here could be a generator.
Okay.
Yeah, could be a transformer. So we are just using very generic notation, yeah, without specifying what it is. Yeah. So the probability of being in the up state, now you can see, is mu over lambda plus mu, right? We spoke about the availability of the component and the unavailability of the component yesterday. Availability is mu divided by lambda plus mu. Unavailability is lambda over lambda plus mu. You may also recall I told you that lambda is a very small number, 1 failures, 2 failures, whereas mu is a very large number, 500 repairs per year, 1000 repairs per year, and so on. So availability must be high, must be close to 1. So it is mu divided by lambda plus mu. So assume that lambda is very small. So mu over mu is 1, right? Almost. So that's why availability is very high, and it is mu divided by lambda plus mu. So this is what it is. Mu 1 over lambda 1 plus mu 1 multiplied by mu 2 over lambda 2 plus mu 2. Probability of component 1 up multiplied by probability of component 2 up. Independent events. You may recall from day 1. Probability of A and B is equal to probability of A multiplied by probability of B, if they are independent, right? If they are dependent, it's different. Okay, so this is what we have as the probability of being in the up state. Now on the right hand side, if I want to take this equivalent component, then what is the probability of this equivalent component being in the up state? Yeah, so that is mu divided by lambda plus mu, where mu s is the equivalent repair rate of this new component, equivalent component, and lambda s is the equivalent failure rate of this equivalent component, right? So I want to find mu s and lambda s. That's my objective now for these two components in series, repairable components in series. So I take that this equation must be equal to this equation, right? I mean, equate the left hand side with the right hand side. The two probabilities must be the same. Therefore, I do some manipulation. Yeah, this is equal to this, so that's this equation. And the transition rate is lambda 1 plus lambda 2. Let me take you back. That's the danger of all these PowerPoint slides. If we can just do this on the board, it's so much easier. But PowerPoint, you have to keep going back and forth. Go back to this slide. Remember the transition rate concept. So if this is the only up state and these are all failed states, what's the transition out of this? What is the total transition out of this boundary? It is lambda 1 plus lambda 2, is it not? So that is the equivalent failure rate, lambda 1 plus lambda 2. So that's exactly what I have here. The total failure rate, transition rate, lambda s is lambda 1 plus lambda 2. And of course, I also want to find Rs. So therefore, I'm going to write mu1 as 1 over R1, mu2 as 1 over R2, and I'm going to try and manipulate this equation, and I will get Rs to be given by this expression. Remember, mu is the repair rate. It is repairs per year, whereas R is the repair time. It is hours per repair. You must see that mu is equal to 1 over R is equal to 1 over mu. Just like lambda is equal to 1 over m, and m is equal to 1 over lambda, right? Mean time to failure, you might recall. Yesterday we spoke about it, okay? So if I manipulate this equation, I expand this, then this is what I will get for Rs, the average outage time of the equivalent component, average repair time of the equivalent component. Now normally you can appreciate that lambda 1 is small, lambda 1 times lambda 2 is even smaller. So if we say that lambda 1, lambda 2, R1, R2, that is this term, is much smaller than this one and is much smaller than this one, then we can assume that this one can be neglected. Yeah? And therefore I will get Rs is equal to lambda 1 R1 plus lambda 2 R2 over lambda S. So this is the approximate equation that we use for series components in power systems or anywhere. You can be talking about pumping stations, for example. It's the same. The concept can be applied to even mechanical systems where components or elements are arranged in series, or they're operating in series from a system standpoint. Yeah. So the equations now can be generalized like this. The equivalent failure rate of a series system is a summation of the failure rates of the individual components, lambda 1 plus lambda 2 plus lambda 3 plus lambda 4. And the equivalent repair time or outage time is equal to summation of lambda I Ri over lambda S. Yeah, remember this equation? Lambda R plus lambda R. So summation of lambda I Ri over lambda S. So I have generalized these equations. We have now the effective failure rate, we have the effective outage time. And therefore the probability of being in the down state is now calculated as Fs times Rs, frequency times the repair time. Yeah, where F is the frequency. Remember, F is frequency, lambda is the failure rate, right? The two are slightly different. I even showed you an example yesterday where we got the lambda to be 3.02 when the frequency is 3 times per year, right? So they are slightly different. But if we look at the mean time to failure and mean time between failures, and if we find that the two are almost the same, then we can argue that the frequency is approximately equal to the failure rate. 3.02 is approximately equal to 3, correct? That's all I'm saying. So if that is the case, the unavailability U is equal to lambda times R. Yeah? So this U, the capital U, is normally called as unavailability of the series system. And of course, lambda, you know by now, is the equivalent failure rate, and R is the equivalent outage time. Okay? So an example will always help to illustrate once we go through the series and then parallel systems. So let's look at the parallel systems now. We have two components, repairable components connected in parallel from a system standpoint or operating standpoint. The first component has failure rate lambda 1 and repair rate mu 1. The second component, the numbers are lambda 2 and mu 2. And I want to find an equivalent component where the failure rate is lambda p and the repair rate is mu p. P stands for parallel, right? I mean, that's the notation I've been using. So if these two are in parallel, and I take you back to that 4-state Markov model, sorry, this one. If the two are in parallel, then this is up, this is up, this is up, only this state is down, right? So I have all these three which are up states, and only this state is the down state. So what is the transition rate from the down state? The transition rate from the down state is mu2 plus mu1, correct? So therefore, that particular equation that I was about to show you, the transition rate is mu p is mu1 plus mu2. That's the transition out of the failed state, where mu p is the transition rate from the down state of the equivalent component, right? And then what else can we write? What is the probability of being in the down state? What's the probability of being in the down state? Let's go back to that diagram. What's the probability of being here? The probability of being here is the probability that component 1 has failed multiplied by the probability that component 2 has failed. And what's the probability of failure? It is lambda over lambda plus mu. The probability of being up is mu over lambda plus mu. But the probability of being down is lambda over lambda plus mu, right? So therefore, the probability of being in this state is lambda 1 over lambda 1 plus mu 1 multiplied by lambda 2 over lambda 2 plus mu 2. So that's what we'll get. Yeah, so lambda 1 over lambda 1 plus mu 1 multiplied by lambda 2 over lambda 2 plus mu 2, correct? Now I can equate this side to the equivalent component, where the unavailability of the equivalent component will be lambda p over lambda p plus mu p, is it not? I'm trying to say that this system is equivalent to this system. Therefore, these two equations must be equivalent. So we can find, using mu p is mu1 plus mu2, we already know this. I now am interested in finding lambda p, right? We want to find the lambda and mu of the equivalent component, right? Which is what we did just now for the series systems. So we already know how to calculate the mu p, but how do we calculate lambda p? Just expand this equation and then try and manipulate, and you will find that the lambda p turns out to be of this form. The lambda of this parallel system turns out to be of this form. Now once again we make an approximation. We say that normally lambda times r is much less than 1. Lambda times r is much less than 1. Therefore I can neglect this, I can neglect this. So in the denominator I am left with only 1. And therefore lambda p is lambda 1 lambda 2 times r1 plus r2. Okay? So that is the effective failure rate of two components operating in parallel. And the effective repair time, if you want the time, it is r1 r2 over r1 plus r2. If you want the repair rate, then it is mu1 plus mu2. Of course, either of these equations can be used because we know mu is equal to 1 over r. Okay? Now, be a little bit careful when you use this equation. Remember what is lambda? What are the units of lambda? What are the units of lambda? Anyone? I should do this more often. Pause and ask. Failures per year, very good. So failures per year times failures per year, right? And what is the unit of R1 plus R2? Units. Hours per repair, very good. Hours per repair, yeah, or hours per failure, right? So if you expand this, you will find that the units are not matching because this one is in hours, this one is in failures per year, right? So you need to convert this into years, okay? And therefore you need to divide by 8760. Yeah, so that's the tricky bit here that you need to be aware of. And when a little later, when we see that there are three components in parallel, you will find that the equation has lambda 1, lambda 2, lambda 3, and then over here is r square. So therefore you will have to divide by 8760 twice. Okay? Just to alert you that that's going to happen. Okay? So these are the equations for the parallel system. The equivalent failure rate is lambda 1, lambda 2 times r1 plus r2. The equivalent repair time is r1, r2 over r1 plus r2. And unavailability is lambda times r, as we said for the series system. Assuming that the frequency is the same as the failure rate, then it will be lambda 1, lambda 2 times r1, r2 because this will get cancelled, right? R1 plus R2 will get cancelled. So these are the basic equations of components in parallel, just like we derived the basic equations for components in series. Now, obviously, there will be more components in the system. I mean, we are talking about power systems. We don't have just 2 generators in the system. We probably have hundreds of generators in a large power system. So that's why we always rely on these Markov models to get to that stage where there are so many states that you have to program it. There is no other choice. You can't use just equations in a simple manner like this. But let's just look at 3 components in parallel, because that is still doable by hand calculations. So the equation for 3 components in parallel turns out like this. But let me show you how we derive that. There are 2 possible approaches. Replace components 2 and 3 by an equivalent component. So I'll show you the diagram here. So these are the 3 components assumed to be in parallel, right? Lambda 1, mu 1, lambda 2, mu 2, lambda 3, mu 3. And of course, mu and r are each other's reciprocal. So therefore, now I'm using lambda r, lambda r, lambda r. So I want an equivalent component of 2 and 3. Equivalent of 2 and 3. And I know how 2 and 3 in parallel will behave, right? Just now I derived the equations. So what is the equivalent lambda of that? It's lambda 2, lambda 3 times r2 plus r3. What is the equivalent r for that? It is r2 plus r3. R2 plus r3. There's something wrong there. It's r1 r2 over r1 plus r2. So it should be r2 r3 over, should be r2 times r3 over r2 plus r3. Sorry, this is obviously a mistake. R2 r3 over r2 plus r3. And then you can combine these 2 in parallel using the same equations, right? You can extend the analysis. Perhaps a simpler way is to look at this table. This table tells us how to actually write the equation more easily. So you look at the ways in which the system can fail. First failure, component 1. The second failure is component 2 when? During the repair of component 1. So in other words, component 1 is operating and it has failed, and then component 2 has failed while you are trying to repair component 1. Yeah? And then the third failure happens. The third component fails while you are trying to repair 1 and 2. Right? We call this overlapping repair, meaning that there is an overlap in time. Doesn't matter at the same time, but while you were repairing 1, 2 also failed. So now you are repairing 1 and 2, and there is an overlap between the 2. So there are 6 possibilities. First failure, component 1. So you look at this equation. There's a very nice way of writing this equation. First failure, lambda 1. Second failure, component 2, lambda 2. During the repair of 1, R1. Can you see the trend? I repeat again. First failure, 1, lambda 1. Second failure, component 2, lambda 2. During the repair of 1. During the repair of 1. Third failure, 3, lambda 3. During overlapping repair of 1 and 2. Overlapping repair is R1, R2 over R1 plus R2. I show you one more, for example, the last one. Yeah? First failure, component 3. It has gone to the next page, so we can't do that. Let's use the fourth one here. First failure, component 2, lambda 2. Second failure, component 3, during the repair of component 2. Third failure, component 1, lambda 1, during the repair of 2 and 3, R2, R3 over R2 plus R3. So that's how you can write the 6 expressions, and then of course you can solve them, and the ultimate expressions are like this. Mu p for parallel system will always be mu1 plus mu2 plus mu3 plus mu4 whatever. So therefore rp comes straight away from here, and then lambda s can be approximated using this equation, and system unavailability is lambda times r. So up to 3 components we can easily do the hand calculations. Beyond that it will become harder for us, right? So we will again need to do more approximations, right? We go back to our favorite method, the minimal cut set method, also known as failure modes and effects analysis. Yeah, it's a very, very powerful technique. because you can program it on a computer very easily, regardless of the number of components. Okay? So we have already dealt with this. You may recall that when we talk about the failure modes, the cut sets, the components of a cut set are connected in. The components of a cut set are connected in series or parallel? Components of a cut set are connected in parallel, and each cut set is connected in series. So we have that background with us, and we are now going to look at a system where all the 5 components are identical. Now this is just to save us some time for calculating. I can easily give you 5 different reliabilities, and then your life becomes a little bit harder. But we don't want to do that at this stage. And have lambda is equal to 0.05 and R equal to 20 hours. Calculate the system indices of average failure rate, average annual unavailability, that is U, capital U, and average outage duration, that is R. Okay? So lambda, R, and U, these are the standard indices for reliability evaluation, as you shall also see over the next 2 days. Whether you are dealing with generation systems or transmission systems or distribution systems, the most basic reliability indices are those of lambda, R, and U. Failure rate, average outage time, and average annual outage time, which is also known as unavailability. Okay? So what are the cut sets of this system? We actually did this system before, right? We used the same example before. So what are the minimal cut sets? 1 and 5, 2 and 5, and 3, 4, 5. There are no first order cut sets, correct? There are 2 second order cut sets and 1 third order cut set. So second order cut sets 1, 5, 2, 5, third order cut set 3, 4, 5. So if you recall the equation of 2 components in parallel, and I repeat again, the elements of a cut set are connected in parallel. We must use the equations for parallel. Just now we derived them, right? So a second order cut set, the equation you remember, lambda 1, lambda 2 times R1 plus R2, right? So here the elements are 1 and 5. So lambda 1, lambda 5, R1 plus R5. Now, since all the components are identical, lambda 1 is same as lambda 5. So this becomes lambda square. And R1 is same as R5. So this becomes 2 times R. And then I substitute lambda, which was given to us. It's given as 0.05 failures per year. And R is given as 20 hours. So 0.05 square times 2 times R divided by 8760. I already explained that to you, right? So R is very easy. It's R1, R2 over R1 plus R2. Turns out to be 10 hours. Similarly, you can do the calculation for cut set 2. Yeah, it will turn out to be the same because the components are identical. And then the third order cut set, you have to use the equations for the third order 3 components in parallel, which we derived just now. Yeah, so lambda is lambda 1, lambda 2, lambda 3 times R1, R2 plus R2, R3 plus R3, R1. Yeah, and Rp is given by this equation. So you can just substitute. Notice again, you divide by 8760 square here. Yeah, because this is square, yeah, R square. And R is in hours per failure. Okay, so that's the most important thing. Otherwise, you will not get the right value. Okay, and the average repair time is just 20 hours divided by 3 because they are all in parallel. Okay, so we can write it in the form of a table. Yeah, this is cut set number 1, 5, 2, 5, 3, 4, 5. The lambda for that cut set, the unavailability for that cut set, and then you want to find the effective R. Then it is U divided by lambda. Yeah, it's U divided by lambda. Okay. From this you cannot determine 10. So how you determine the average outage time? That is average annual outage time divided by average failure rate. Okay. So these are the 3 indices that we need to be aware of. I just want to make a few comments before we move on with other ways of looking at it. The indices of lambda, R, and U are usually dominated by the lower order cut sets. You look at this lambda 1.14, whereas for a third order cut set, it's e to the power minus 9. Even the first one is actually quite small, but e to the power minus 9 doesn't make sense to include it, right? So the domination is coming from the lower order cut sets, so we could ignore the higher order cut sets. Then minimal cut sets, we know already by now, they define the failure modes of the system. We know how the system will fail. If components 1 and 5 fail, system fails. If components 2 and 5 fail, system fails. From this discussion, we know that the impact of each failure event can be determined, and therefore we can decide where we want to reinforce the network. Maybe the failure rate of components 1 and 5 is too high. Maybe we want to reduce the failure rate. Maybe we want to reduce the repair time. Instead of 20 hours, maybe we want to make it 10 hours. So these are ways in which you know how the system can fail, and therefore you can also think of ways to reinforce the system. Okay? The most important aspect when evaluating reliability is to have a complete understanding of the engineering implications of the system. Probability theory is only a tool. I'm not suggesting by any stretch of the imagination that all of us should become probability engineers from today. Yeah, it's just one of the tools. There are many, many other tools that are available, including machine language and artificial intelligence tools. A lot of people have used fuzzy logic to do all these calculations in reliability for the last 5 decades. Yeah, I'm not a great believer of that, but it still exists. That's a different matter. So probability theory is just a tool for engineers like us to transform the knowledge of the system into its most likely future behavior. Again, most likely future behavior. It is uncertain. There is no 100% certainty that you will be able to predict the future behavior of the power system. So the basic steps involved in actual reliability analysis can be summarized in this particular manner. Understand the way in which the system operates. Identify the ways in which it can fail. And then evaluate the consequences of failures. Are those failures acceptable? If they're acceptable, then we don't need to worry too much about them. But if they're not, then we should know what the consequences are and how to deal with them. And then derive models to represent these failures. What kind of model are you going to use? Approximate model, detailed model? Yeah, things like that. And last but not least, now you select the reliability evaluation method. So reliability comes things before. You must know your system. You must know the weaknesses in your system. You must know the strengths in your system. And something that is inherent in data. If you do not have enough data from your system that you have collected over the years, then I think all the analysis is probably of no consequence. It's like garbage in, garbage out. So data is so very important. Statistical data is important because you can then use it to predict the future performance. That's why we don't rely on deterministic, we rely on statistics. This is real, right? Yeah, that data was collected, so it is real. Okay, so I think on that thought, we finished this particular chapter, which we started yesterday, so we are slightly ahead of time, but that's always good, right? Yeah.